Hi everyone, my name is Gabriella Courier. Today we're working on exam 2 for Transport 1. And we will be writing a code to solve for the following network. We want to calculate the water flow in each pipe or through each pipe segment and net flow in and out of the source and sink, which is our first node and our fifth node. Then we know all elevations are at 0 meters, except for at node 0, which is at 30 meters elevation. Node 4 is fixed at a 0 Pascal for pressure. Node 0 is set to 200,000 pascals pressure. We know the diameters of all pipes are going to be 0.1 meters and with a relative roughness of 0.001. Right, and then we have our array of values here for our pipes, and we will include that later in our code. So go ahead and get started here. Before I start my code, we also have our we have our formulas over here written out and recorded. So we know that our Bernoulli's equation, our first half of our Bernoulli's equation is going to be our delta head. So our change in head between each node, so our change in direction from each pipe, through each pipe to each node, sorry. And then we just added in our friction factor formula and set that equal to our Bernoulli's equation. Alrighty, and then we have our formulas for our volume, our Reynolds number, and we'll get to that one later. So, first things first. We're going to import numpy as np. Stop doing that. And our function. This is going to allow us to use some basic algebraic functions and symbols in our code. Next, we're going to set all of our constants that we'll be using for our equations. So we're going to be using our gravity constant. It's going to be 9.81. Rho is equal to 1,000 meters. Mu is going to be equal to 0.1 meters. I think that's right. 0.01. So rho, we have our diameters, which are set equal for all. .1. And then our roughness factor, which is going to be equal to 0.001. I'm pretty sure. Looks right. All right, so these are going to be our constants. Now that we have those put in there, the next step in our code and solving the problem is we're going to use the Churchill correlation equation to predict our friction factor. So we want to solve for our friction factor because it is the only unknown we have right now. So we have our pressures, we have our rho constant, or value for rho, we have our gravity constant, our change in positions for our delta head. So those are all known. And then we know our K, it's an arbitrary value, it's a constant. We know our roughness factor, and we know our volume in here. So really the only thing we need to solve for at the moment is our friction factor, in which we'll be using the Churchill equation to solve for that. And so what we need to do is put in our code, do a side by side, make this a little easier. That's not my code. All right, so we're gonna calculate this. We're gonna define function of Reynolds number and our roughness factor. We're gonna put in A, equation for A. It's gonna be 2.457 times NP log log is inverse. Okay. 1 over 7. It's asking for 1 over 7 divided by Reynolds number raised to 0.9 plus 0.27 times E, our roughness, and then make sure we have enough parentheses there. Is that to the 16th power? For B, it's a little simpler to put in there. B is going to be equal to 37,500. I hate number one. 37,530 all over Reynolds number. All right. So now that we have defined our Reynolds number and our roughness factor, well, not Reynolds number, we're just going to put in an arbitrary value for a Reynolds number or a value given to us. But we already have a set roughness factor for this problem. So that is defined. And we defined A and B, and now we are just going to return our formula, our Churchill equation to find the friction factor, which is, write it as 2 times 8. And I think it's going to do 1. Wait a second. No. Yeah. 8 over Reynolds number raised to the 12th power plus, I'm going to do 1 over A plus B, just to get that negative out of there. Put that 1/5 power, negative 1/5 power in the denominator. Make it a little easier on our code. Simply type. Yep. And then is that to 1 over 12. I'm going to say parentheses over here. Sorry, I'm just noticed that. Alright, now we should be good. Let's check this. No, we are not good. Okay. So it's pointing here. I think I need a parenthesis here. Still pointing there? Recording. parentheses here. Okay. Yeah, we were just missing some parentheses. All right, so before we move forward, we want to check that our calculations are working. So we're going to do the function of our Reynolds number. Oh, no, not that. Yep. We're just going to throw in a number. Our roughness. And see if that works. Okay, so that converges. So we know that that's working. Perfect. Right, and then we are going to move forward. Now that we know our friction factor, we want to set our delta head equal to our Churchill equation to solve for our flow rate. No, actually, no. No, okay. Sorry about that. We're going to set our delta head equal to our equation, our friction factor equation, now that we've solved for that unknown, and we want to solve for our delta head next. All right, so we want to use, this is where we're going to use our volume, our volume and our Reynolds number equation to solve for that delta head. So we're going to go back to our code. Okay, so this we can get out of our code because we know that converged and that's looking good, so we don't need that anymore. Next, we want to calculate our delta head. So we're going to define this function as d head, no space. So we know our flow rate, or we don't know. Some values we want to find with this function is our flow rate, our length, and we know our, no we don't, our K value, we know our diameter, and we know our roughness factor. All right, and so next, I don't need it. I'm going to do split screen again. Okay. So I'm going to plug in our equation for our volume. Oh, no. Oh, that sucks. Sorry. I'm going to pause this real quick because I have to find our notes again. Okay. I figured it out. All right, so we're going to put these two formulas into our calculation for delta head. It's going to be flow rate divided by divided by NP pi times diameter squared. I think divided by 4. Or is it multiplied by 4? I think it's divided by 4. So we can close this off for something. Should we go on that, and then RE. It's going to be rho times volume times diameter over define mu, so we can just put mu. I don't know what that means. Foot? Sure. Figure it out. All right, and then we're just going to return our, hopefully you can see this, our friction formula. Or not our friction formula, our equation right here. So if we set it equal, it's going to be returning negative K value. Okay, keep it constant. Capital K value plus 4 times F R E E D plus times the function of our Reynolds number and roughness factor. Apologize about that. Times the length over the distance. I got the point. Alright, and then we times that by our velocity squared. Divided by 2 times the gravity constant. And that should be good. Let's see if that works. All right, it's saying it's good, so we're going to test it. Just test it real quick. Just why not? All right. Test it. Alright, our function of delta head. We're just going to give it some numbers for the flow rate, the length, and the K value, but we do know our diameter and our roughness factor. So I'm just going to say 30, 10, to 12, and then we know 0.1, and that's 0.001. Great, yeah. Let's see if this runs. All right, so that looks good. So since our flow rate is positive, since our flow rate is positive, and we got a negative value, very small value, but negative value here, that looks good because we have a little diagram to make it a little easier to explain. Let's say from node 1 to node 2, in a positive direction, they'd be going towards 2. But if there's a change in direction going from 2 to 1, that would be a negative. So this looks good right here. Let's just throw negative in here to test the opposite. Okay. So we need to fix this because it's looking correct when it's positive. Get a negative, but if we're going in a negative direction from node 1 to node 2, from this to this pipe, it should be in a positive, so it should be the opposite every time. And so how we do that is we want to account for a negative flow rate and our volume. So we're going to use the function. All right, yeah. So let's go ahead and use NP absolute value. What does that do? Cool. Oh, cute. I think I need to single this out. Maybe a parentheses here. We'll run it again to see. Okay. So our syntax looks good. And then also, if you've been watching my videos, like in homework 4, we need to account for a sign change in our calculations. So how we're going to do that is we're going to go here in our function, in our equation, and do NP signage, I think. Let's see if it corrects me. K plus 4. Don't think we need another. Okay, it looks. It's allowing me to do that, so it looks good. All right, and then we're just gonna check that. Whoops, we did something wrong. I apologize. So, to use the signage, just kidding. So, there's no such thing as signage. All right. Negative NP sign. And that should be the right way because it's telling me here that there's no attribute signage, so I kind of just made that one up. That's no good. Let's see. Maybe missing a negative sign somewhere. It should not be the same. So that's right, but we still are wrong in our negative flow. It's not going to a positive flow, so we need to fix that. And I think from lecture, maybe we don't need this negative here. Okay, so we just didn't need that negative because we have NP sign. All right. And then let's make sure it's all other ways correct. We do need a negative sign. Where do we need it? Here? Is it here? Should I not have touched that? Okay. Grr. I know there needs to be a negative sign somewhere. Alright. So my Google froze a little there, so okay, sorry. Computer's run a little slow. Probably gonna unplug it. It's been on the charger for a while. So what we did to fix this problem, because as you can see, when I have a negative flow rate, I get a positive delta head. And then we're going to test that again with a positive flow rate, and we get a negative delta head. So like it shows a change in the flow rate. But basically I put a parenthesis here and here, which was not needed. A little bug on my coffee. Yeah, and then I did not need to take away that negative. we went ahead and put that little guy back there. All right, so now that we checked that, I'm gonna move on to our function of our flow rate. What am I doing? I'll just keep that there for now because I might need it for later. Yeah, so now that we're done with that, we want to find a function to describe our flow rate and our resulting flow rate, which is what we're solving for. So we're going to define V head. No, it's flow, function of flow. V head for our change in flow rate. It's the only difference. And then we're going to do our length, K value, diameters, and relative roughness. That is a semicolon, but okey-dokey. And so we can't exactly solve this yet. There's another step we need to do before that, but we will be returning our resulting flow rate. So we're going to go ahead and write that down because that's something that we know for the moment. Yeah. All right. So we're going to put this, we're going to put our defining or calculating our function for our flow rate on hold because we have to think about, oops, what is that keep just switching? We have to think about our delta head and our function in a steady state. And so we have to think about what value or what initial guess for our flow rate will bring the equation to a steady state, which is 0. And so one way we can do that is our Newton function. I'm going to add new code here. Let that transfer. And we cannot use our Newton function until we define it using our SciPy or SciPy. I keep saying SciPy. Carlos says SciPy. Optimize. We know how to spell because we're smart. I'm going to import our Newton function. I think that needs to be. So now that that is there, we go back down. And basically what we want to do now is we want to find our initial guess. And how do we do that? Okay, so before we make an order to make our initial guess for our flow rate to get our function to go to 0, we need to calculate our volume and our Reynolds number. And so we're going to do that by writing and defining. Writing and defining what do we call it? Our flow, function of our flow. That's right. Flow to 0. Of our Is it a different color? I feel like it's a different color. That looks good. All right. Okay. Now we just put in our volume formula, which is 4 times. We're gonna copy and paste. Yeah, sorry, I was forgetting my absolute value. Can't forget because our flow is negative. So we're just gonna copy these two. Excuse my minutes, guys. Alrighty. And then we're gonna return our delta head. Wait. Where's our delta head? Oh. Yeah. Oh, okay. I see what I did here. Where is it? Here. Okay. So we don't want to get this confused. Our delta head for our flow and solving our delta head. What you call it? We don't want to get this delta head and that delta head confused because this has its own things going on and this guy is doing a different function. So basically we're going to assign a value for delta head. We don't want it to get confused with our calculations for that delta head over here. So we're going to change that to that. We're going to do our delta head plus equation is it? Our function, which is going to be this one right here. I'm just going to copy it, save me some time. Okay, and make sure our syntax looks good. Looks great. Next, we're going to define some variables. Let's see, we're just going to give, oh no. I just took my headphone out because I think it died, but that was my, oh. Okay, if you guys couldn't hear me before, I took my headphone out because I thought it died, but it did not. But what I was saying was we're going to set some values, just some arbitrary numbers for this equation, just to test out the calculations, see if the code is working. Let's just say delta head equals 30. K equals, we'll just put 25. We'll do, I think it's a little, do our length as, let's just do 1.0. Excuse me. Okay. Let's run it. Interrupt execution. So, control MI, so let's just do this. We run like this cell. Alright. So we're running into an error here, which makes me feel like there's something wrong with my formulas up here. So I'm just going to try and do some stuff real quick. There should be nothing wrong with these guys. Just used them earlier. So, okay, now we got that away. So we want to do a guess of flow. Let's just do a guess of flow to 0. Say 10. see if that runs because it wasn't running before. Yeah, it's not running. Maybe this is too short. Maybe we should do 2.0. No, it's perfectly fine. Alright, maybe we should try reading. It's telling me. Okay, so L equals 1.5. Should be pi. Absolute volume. Excuse me. Maybe I don't need parentheses here. That would be the issue, but I don't know how this can be sometimes. No, it's not it either. It's maybe indented. Python input. Input 0Q. Alright, so as always, it might be a spacing or parenthesis problem. Okay. No, still not working. Hurt. Okay. So let's see. Oops. Did I touch anything? No, I didn't. Okay. Just look at my formulas real quick. What is this? Tell me what the squiggly line means. Is this be space? Don't think. No, I still got a red squiggly. Delta head is not defined. Negative maybe? No, that's not it. Alrighty, sorry about that. So I messed up because we don't need to be doing this. We need to make our function for making our flow rate guess, which is our it's gonna allow us to make a more concise. I don't know if that's the word I want to use. Concise guess with a smaller range of values. So we're gonna do that by putting in QGuess. You guessed it. Hope nobody ever watches this other than my professor. Alright, so QGuess delta head, or no. What did we do again? I need my formulas. Alright, QGuess. So basically, we're gonna solve for. I'm gonna solve for the volume in our Bernoulli's equation that we have here for our flow, our network flow. I'm going to plug that in. Yeah, we're going to solve for our volume, and then we're going to plug that into our flow rate equation here. And that is how we're going to make our Q guess. So we're going to do NP. It's going to be a long one. So Yeah, okay. It's gonna be long, so stay with me. NP pi. Sure. Flip. Okay. I wish this error would go away because I think it's out. It's not an error anymore. NP pi. Where's my times our diameter squared times or divided by 4. And then NP times the volume formula, which is going to be NP square root. Negative delta head divided by k plus 1. Oops, no, 4. No, 4. Parentheses times 0.01 times sorry, I just got a text message. I'm hoping that I can hear it in my headphone. I'm just hoping that it didn't record with the video. So, excuse me, I had to pause this really quick. All right, sorry about that. It's the issue of having headphones connected to your phone and your computer. Just 2021 problems. All right, let's finish this. All right, 0.01 times L over D. No, not delta. Don't need your help on this one. Convert a string or number to a floating point number if possible. Don't know what that means right now, but I don't need that to happen. Times 2 times the gravity constant. There's some syntax errors here. Yeah, there is. Alright, let's just look at this real quick. Excuse me. Need more coffee? Code is crashing and I'm crashing. So Q gas equals NP pi times D to square root negative delta 1, 2, 3, 4, 5. Oh, let's see. Okay, so I think I need more parentheses here. Like 2 more. Okay. No. What is an EOF? Let's see. End of your source code was reached before all code blocks were completed. Good to know.